Okay, so we'll start now. I think the attendance will grow over the time. So Sir will talk about today mostly on the security assertion based verification. So initially we'll start with what is basically assertions and what is the security assertions, and then it will build up over the day. Thank you.
Good morning. We are going to talk about trust verification using security assertions. So, the concept of before I talk about verification of security verification, I want to make sure you have the base for what is validation verification, and I am going to zoom into that aspects. Once you are done with that, then I am going to talk about security verification, and then I am going to answer two fundamental questions, which is, if everybody knows all these problems are there in the world, why do not they design things that can withstand all these vulnerabilities? Why do I need to verify? So, I will answer those questions, and then I am going to show how do we verify using assertions. You can verify in many ways, and how do we verify assertion and how that fits into the big story. After I give a little overview of validation and verification, you will get an idea that assertion based verification basically fits into the simulation based validation. So, what happened to the computer? Actually nothing happened, this can happen. So, the key idea is getting a blue screen pretty much freaks out anybody except one set of people. Anybody knows who are these people, or the engineers who actually becomes happy when they see the blue screen? Not the attackers of course enjoy it. Anybody has any idea?
I think those who are not interested.
Yeah, those who want to take a day break and do not want to have class. No, apart from that, so I will briefly talk about post silicon validation. When you fabricate a chip, it comes to the company, you put it on the board, put the operating system, and you expect it to work. Most of the time we do not even get anything in the screen, and it is like that freaks us out. So, we have to do exactly when you write program, the way you comment one of the function, comment another function until you start it printing something instead of giving error. We literally had to kind of turn off, think of motherboard, all the chips are there, you have to literally turn off power supply to each of these selectively until something comes on the screen. So, blue screen actually does not freak me out. Many people are scared of ghost, I actually want to see a ghost. So, the idea of verification boils down the fact that even simple bugs can cost a lot. So, here is a tiny example of a software bug, and as silly as a conversion of 64-bit floating point number to a 16-bit signed number. That conversion, there was a tiny bug in software, and that led to $7 billion in 1996. That is about 10 to 15 billion. So, a tiny error by a software programmer cost that much. So, it is not just in software, even in hardware, a tiny bug in floating point division. If you recall, in FPGA we talk about lookup table, floating point unit is implemented using a lookup, not FPGA lookup, but just a table lookup, and in that lookup there was a mistake. So, lookup table was populated with some values. There was a mistake Intel did populating that table, and nobody would have ever found out until this professor, it is not me, professor spent all this formal verification time and effort to figure out, are there any scenario where this may fail, and found that scenario, and that costed Intel 475 million in 1995. If it was not for Intel those days with deep pocket, any other company would be out of business, and it is a brand name issue. So, any tiny bug, and remember, in a bigger scheme of things, billions of transistor, think of one transistor was wrong with one table, one entry, there was a wrong populated table. Now, it is not just software, hardware, even operating system has a problem. So, this is basically Mars Pathfinder, this is the not the last one, it is last to last one to visit Mars. And when this dude landed in Mars, it wanted to fly. This solar panel you see on top of it, it was opening the solar panel and closing the solar panel, opening the solar panel, closing the solar panel, as if it wanted to fly. and you realize that anytime anything goes wrong with US infrastructure, they think Russia, Iran or China is trying to hack. At least in this case, none of those were happening. If you have taken operating system course, if you know the notion of priority inversion problem, and in a silly example I can explain it to you. So, let us say this is one of the, choose one of the train station, my favorite train station Howrah, and the bathroom is very problematic, and there is one room, one door, let us say one door, and let us say I entered and locked it, and now choose a person who is higher priority than me, Prime Minister of India, waiting outside, very higher priority, significant higher privilege, but until I unlock from that room and get out, I am more powerful than the Prime Minister for that time. Of course, you can imagine breaking the door and all that stuff if you ignore that. So, that is the scenario happened. There were 3 tasks, 3 programs, think about it, 3 programs running, task 1, task 2 and task 3, and task 1 is higher priority than task 2, which is higher priority than task 3. And what was happening, that the task basically 3 is basically it executed a semaphore. If you have studied semaphore, it executed a lock. Think of that bathroom and closing the lock, and task 1 comes in. Ideally, it wanted to preempt task 3, so the task 3 stops, context switching happen, task 1 starts running, but because it got the lock for a mutual exclusion and these two operates on that data, mutually exclusive data, task 1 had to wait. In between, task 2 came in, who has nothing to do with that shared section, and it basically continued for a long time. Then control came back here, then this one executed unlock, and only then this one got, this would have got the control. And there was a security mechanism in that, that when this data collection is happening, enemy countries of USA or not friendly countries of USA should not steal it. And because this task is a highest priority task and it takes only, let us say 20 millisecond, if within 30 millisecond or whatever 1 second it does not terminate successfully, system will shut down as if somebody is stealing something. That is what was happening. It opens the wing, wanted to transmit something, but in the meantime this task 2 comes in, one of the communication tasks which has nothing to do with the business, but because of this precedence and all that, this is called task inversion, priority inversion. You become king for a day because you can block the king, right. Now, fortunately the problem was solved as soon as they figured out. Operating system also has a concept how to solve it. If somebody blocks a higher priority task, at least for that duration until it releases the lock, it becomes higher priority or equal priority, T1 equal to T3, higher priority than T2 for that time frame. So, therefore, in that case T2 will try to attempt to take the control, but T3 for that moment is higher priority, control will continue, it will do the VS and then control will go back. So, this flipping thing. So, priority inherent switch, they turn it back. Now, this is technically not a bug, solution was there before Mars Finder was sent to Mars, they forgot to enable it. But the point I am trying to make, I took only 3 examples just to illustrate the point, whether it is a tiny software error, tiny hardware error or even tiny operating system bug or forgot to set a switch, it can cause havoc. So, now before I talk about verification, we talk about hardware, software, firmware. One of the chip most people focus on is this system on chip, we call it system on a chip, and it basically have a typical automotive SoC would have around 100 to 200 component, and each of the component, major component is always a processor, then there could be voltage regulator, bridge and tons of stuff, controller, adapter, lot of different types of memory depending on the system, and this is kind of the peripheral bus, and all these are standardized. So, that you can buy, you as a system designer can buy components from multiple parties and put on the bus, right. So, this is the kind of chip And if you look at when different companies chips look different. So, if Qualcomm is building their chipset or Broadcom building their chipset, Samsung, Apple, they look different, but if you take the summary of it, this is the summary. Half of them fail the first time. So, you design something, send it to the fabrication facility, bring it back to your facility and test it, it does not work. It does not even give a blue screen, it just does not work. So, that we call as first silicon failure. And if you look at the first silicon failure, the scary part is half of them fails. If you look at those half of them, out of half of them, how many of them failed, for what reason? This is a worldwide story. Some SoCs are tiny, they may not fail that much. Some SoCs are very complex, they may fail more, but this is an average. If you look at it, do any of you see anything funny? So, again let me put the number there for you to kind of understand. So, about 50. Oh, that line is a next page. Okay. About 50%. Oh boy, I can write 50. Sorry, say again.
You select the pen.
I thought okay. Let me do that again. Oh, pen was not selected. About 50%. 50% fails first time. Right. So, let's just digest that fact, which is a very scary fact. Fabrication is very expensive. I can get into the detail. Each fab cost in the order of billions, 2 to 10 billion to build, and they will be obsolete in like 2 to 5 years. So, they have to make up all of that money in that tiny time frame. Like in 3 nanometer technology, the fabs that are running, you have to understand the particle size, dust particle size cannot be bigger than 1 nanometer. So, they have the filtration mechanism, air conditioning mechanism has to accommodate 1 nanometer size particle. So, that is the clean room, that is the most expensive part. People think this photolithography, drawing transistors, sure those are expensive too, but really this whole chemical process of making that clean room is the most expensive part of the story, but not whatever it is, 50% fails. Out of that 50%, this is the story. If you add up, this is supposed to add up to 100, unless I made anything wrong, it is supposed to add up to 100. Now, do any of you see anything funny here? So, these are the reasons. So, for example, if I choose firmware, so failure happened because of firmware is about 10% of the chips, 10% of these 40. So, this is 10% of 50%, which is 5%. 5% of the chips failed because of some firmware problem. So, let me start the discussion. That is actually not a scary thing, because firmware patching is easy. You just change the firmware, update the firmware, problem is solved. Anything funny you see in this diagram?
Safety feature and security feature data is pretty limited.
Safety security feature data is limited, that is interesting, because these numbers are 2020, people are not taking them seriously. Anything else you see here? How come the big things does not show up to you? Almost 50% of them, which is 25% overall, is failing for logic or functional bugs. I can zoom into any of them, talk for hours, I will just want to zoom in this for today. Functional error, that means you designed an adder and it is not adding correctly. What would be your first impression? That means you wrote a program, you did not test it and you just gave it to your customer. Do you think that is correct? No, right, that can't be true. So, we are trying to dig in what exactly then happened. Why so many of the failures are due to functional errors. But I want to spell one more thing, delay is not here. When you think of functionality, delay is also important, because what is not correct is that you give an adder and it add 2 and 3, what should be the output? I want to see hands. If you add 2 and 3, how much it would be? I want to see hands. I want to see all hands. I want to create a practice that you guys raising hand. I would have loved to see both hands. Doing exercise is good, it is 5, right. So, the thing is, even if the adder produces 5, but it does not produce in 1 clock cycle, that is actually bug, that is a problem. Why wouldn't it not produce? Because remember, this is not an electrical class, but just to explain, if there is an AND gate, there is a delay associated with, let us say it is a 1 nanosecond. Because of the fabrication technology, because the temperature on which the computer is operating right now, the delay will change, the parasitic capacitance will change, and it is a charging and discharging, and charging and discharging, it is e to the power t over r c. So, it is not like straight goes up, it takes some time to get to the value that we believe as 1, glass becoming full, and that is 1 nanosecond delay in layman terms. And if the temperature is high, it takes longer to charge. If the fabrication is slightly deviated, process variation, then it will not be 1 nanosecond. So, if it is a longer than 1 nanosecond, it is going to take 2 clocks. So, even if it 2 plus 3 produces 5 in 2 clocks, that is not good. That is treated as, because everybody else is waiting for that result. At the end of 1 nanosecond, somebody else reading this value is getting a garbage and is continuing with that garbage, its overall thing is garbage in, garbage out. So, that is not acceptable, right, makes sense. Okay. So, now I am going to zoom in. So, basically this is also treated as a functional bug. In fact, even if which I am not planning to talk, even if power, right, this power thing, dynamic power management, that is almost 30% of the logic. Think of, you wrote a program, 30% of the program is power management, dynamic power management, dynamic voltage scaling, all that. If the power management functionality was implemented incorrectly, it was supposed to turn off, let us say a controller, by mistake it turned off the processor, right. So, then it is going to produce wrong output. Your logic is correct, but eventually it will show up as incorrect output. So, no matter what it is going to lead to incorrect output, but I am going to just focus on not these indirect ones, the direct ones, and I am trying to give you an answer why so many of them failed. One of the reason is there any course in IIT Guwahati on verification? There is one, okay. So, make sure you take that course, because most people, we have this social mindset that verification or testing is a bad thing. I keep hearing engineers talking, oh you are lucky, you got into design group. Yeah, I was in testing group. Give me a break. You want to go enter, you do not know anything, you want to start designing and you expect that to be successful. In fact, if that is successful, many companies will use it and they will find bugs, somebody has to fix it, and you do not want to fix it. You do not want to clean up your own mess. It sounds very funny, and you want juniors to fix it, but when you are junior, you do not want to fix it. To me, it seems like very non-intuitive cycle. In fact, what I will say, company has done enough they could do. In 1995, this is again an average of the worldwide average. So, 1995, a typical design used to be 1 million gates, think of 1 million line of code and 20 engineer years. 20 engineers here, you can think of 5 engineer for 4 years or 4 engineer for 5 years, whichever way you, it is definitely not 20 engineer and 1 year, which is now. Now, most of the designs have 1 year life cycle, then it would be 20 engineer 1 year. An important part is every design typically used 100 million tests that ran. 2001 10 billion tests, 2017 1 trillion tests, 2024 these numbers are available, billions of transistors and trillions of tests. This number is not available, I just put that in. My finger also does color, nice, this is very good, right. So, that is the story. Now, I am going to ask 2 questions at this point. I want everybody to raise hand. We know 2 things, no, professors are not allowed. We know 2 things for sure, that 50% of the failures are because of logic bugs. We know that. We also know what the industry is doing or industry was doing in 2007, was doing in this. Why didn't they do more? If you knew, if I do this much, that is not good enough, why didn't they do more? So, why did the top stop at 1 trillion? Why not 10 trillion? I do not know whatever the next number, gazillion, whatever it is, why didn't they do that? You can run in cloud, it is not that expensive, and of course, it is all relative, right, cost. Would you be paying $500,000 or $1 billion for fabricating second time, or would you just take some cloud resources, use 100 or 1000 more computers or million more computer for few days, and that would be much cheaper. Why didn't they do it? I am expecting all hands from the students. I am seeing only one. I am not happy. Go ahead.
Sir, one reason could be that they want to shorten the life cycle because of the competition part. So they try to push in the product and then eventually give out the patches so that they can kill the competition.
Okay. That sounds good, but did any of you realize managers always get paid more? PhD students always do the work, professors always get paid more, they get all the awards, all the recognitions. Didn't ever bother you? It always bothered me, in industry. I do all the work, and the people who have tea with the bosses, they get all the salary hike, and that actually true even here. First of all, managers are incompetent, take it from me, tell it anybody, they are all incompetent people get promoted, because they have time and energy to do the necessary oiling to get promoted. And then what happened? All they do, every company you go, that is all they do. They plot over the time, let us say in last week, last day, how many bugs were found, they plot, and let me tell you how fundamentally flawed that is. And plot would typically look like this and stuff. I did not make it 0 because even if you did not find any bugs, that does not mean there are no bugs, right. So, I will get into this plot. The fundamental flawed problem is, first of all, people are reluctant to report bugs in their own design. They will just fix it and forget about it. That is one story. Second is, if you are not finding any bug and your boss is manager is pushing, please give me a thumbs up so that we go for next stage, layout, fabrication, and then there is all this pressure from the customers, when are you going to give it? So, there is all of that stuff. But then the bigger problem is, even if you ran lot more computers, let us say you used 1,000,000 computers and there is only one bug, it will fail in all 1,000,000 of them, and depending on who is running it, from operating system guy, processor guy, the programmer guy, it might the same bug will show up differently in different places. So, we need 1,000,000 engineer to debug them, and then eventually we will find it is the same bug. So, that is not possible, that is simply not possible. Just the ability that I can run million or trillions of test case and trillions of them, and when it fails somebody has to analyze it. We do not have that manpower, computer would not do automated analysis for you. So, that is a real problem. Now, let us come back to this manager's dilemma problem. So, if manager is not seeing anything, what is supposed to do? Then they go by statistics. Statistically, last year my competitive companies, everybody did this much, last few product generations we did this and we were fine, we will be fine. Literally that is the do. And just for between you and me, manager also do not plot this, their secretaries do. So, it is not actually clear what managers do in these companies, get all this money, right. They will make you form all these TPC report, they will force you to go to certain meetings, and when you realize, then come for PhD. Before that, I want you to get that pain, because I am not able to convince you academia is the right thing for everybody doing research. So, now let me ask two questions. Now that you understood what I said, why this bump happened? What does this bump mean? Number of bugs in a particular day or a week suddenly gone up. What does it represent? Nobody is raising hand. It basically represent all the components are now working, they are talking to each other, and that interactions basically produced a lot of bugs. So, when I am designing an adder, Dr. Karfa is designing a multiplier or operating system, each of them are fine, but when you put them together, their interactions, whatever stuff, that kind of opened up certain bugs that was not otherwise possible to see, right. Why did it go down? What does this point represent? You found the bugs, you fixed them, of course it will go down. Why did it go up, whether this one or this one? Why did it go up? If it gone down, it is supposed to stay down or at least oscillate right there. Yes, please. Who was saying?
Because that patch may also have vulnerability in them.
Two things. One is the bug fix might introduce bug, but most of the time based on my experience, bug fix actually exposed some other bugs, which was earlier getting, let us say, going through AND gate, one of them was 0, because one of the line is 0, this was getting masked anyway, because output is 0 no matter what. Whether this one is supposed to be 1 or 0, it will mask it, but this bug fix actually exposes certain other bugs. But whatever it is, that is the problem. So, bottom line, these functional bugs, it is not because nobody was doing anything, because people were doing whatever best possible, and that is one of the reason people do formal verification, which I will introduce in a moment. By the way, anything I am talking about, all of them are applicable for security verification. I will formally bring them back. So, verification complexity for SOC kind of domain, SOC firmware hardware domain is 70%. So, that actually would bother you. Why in computer science, at least IIT Guwahati has a verification course, many departments do not even have a course on verification. So, that would bother you. If 70% of the world story is verification, why it has less than 1% representation in the story, but that is not for us to decide. But to understand an adder, if each of the line is 64 bit, can anybody tell me, it is a 64 bit integer, how many test cases do I have to try to completely verify this adder? Hands please. If each input is, if you are still blinking, let me show you an analogy. This is an AND gate, I have 2 input, each of them is 2 bits. How many inputs are possible?
4.
How did you get 4? Who said 4 on this side? Yes ma'am, how did you get 4? 2 into. So, there are 2 possible choices here, 0 and 1, here is 2 possible choices as 0 1. So, you basically 2 multiplied by 2. So, that is how we got 4, or we can view it 2 to the power 2, right. So, 2 to the power 2. Now, sorry, let us not go into 2 to the power 2, it would confuse. Okay, so 2 times 2. Now, anybody help me out here, how many possible inputs are there? 2 to the power? No, 12 will not work. 64 is each of the 64 bits is each of the input. Anybody else? No, professors are not allowed. Anybody else? 2 to the power? So, there are 2 to the power 64 possibilities here, 2 to the power 64 possibilities here, here is 2 to the power 64 possibilities here. So, then this will be multiplication of them, all possibilities of this. So, then total choices are 2 to the power 64 multiplied by 2 to the power 64. Can anybody help me, how much is this? 2 to the power 120. I like that, but you started with 12, but what happened to the 8? You forgot? 2 to the power 128. Can anybody tell me what it is in 10 to the power? So, you guys 32, how did you get that number? God, 2 to the power 10 or about 1024, which is 1000, is about 10 to the power 3. So, you do not need to be a genius to figure that out. 1024 is about 1000. Anyway, so I am not going to clean it. So, this is around that number 3 to the power 10 to the power 30. I want you to take a blink and think 10 to the power 12 is a trillion. There are about 200 billion trillion stars in the universe. This number is much larger than that. Even all the computers in this world running forever will not be able to try all possible inputs for an adder. Just verifying an adder completely, all possible scenarios. And that is where the question is, if verifying an adder is impossible, what is the hope we can verify an arithmetic logic unit, which is an adder, subtractor, multiplier, divider. If I can't verify that, what is the probability I can verify a processor? If a processor I cannot verify any systems, even in the airplane we fly or a car you drive or the phone you use, do not even think about it. I can assure you the airplane you fly or I fly, 99.999% of it is not verified. Now comes the interesting question, I want all hands here. my chances of dying in a lightning strike when I go out of this building is higher than dying in an airplane crash. So, airplane is that safe. How can you explain a device with millions of lines of code not verified, nothing is verified, it is completely bogus thing, has so much reliability? How can you explain this? Absolutely garbage, but huge reliability, and in fact most safety critical systems have huge reliability. How come? So, if I draw a, if you know Venn diagram, if I draw a Venn diagram, if this is the space of all possible scenarios, it is probably a tiny here, maybe little bit there, this is all verified in a airplane, that is all is verified. Up to the, it is still not up to the scale, very tiny kind of scenario is verified. How come it is still so reliable?
So, probably because they have priorities on which test cases are most important and hazardous. So, they run those in first.
Absolutely. So, I am trying to involve everybody. Why is it a rocket science to you to answer or participate in this discussion? In fact, one of the danger you are doing to yourself, most people say, oh, it is a rocket science, you will not understand. Rocket science is actually trivial. If I teach a class on that, you will figure out it is trivial too. It is just that some community of people want to keep their ego boosted and they say, oh, this is very complex, and you are supporting them as a social engineering, you are falling in their trap by not participating in this discussion. Please participate. What would be the wrong? You will give a wrong answer, it does not matter. You want to push forward and become famous, right. So, the way you do is participating and brainstorming. So, the reason it works, before I go there, let me go to the Apple's philosophy. Adder verification is not possible. Intel still tries to verify all possible combinations in a processor in some manner. I will show that when I talk about formal verification. Apple said, we do not want to do that. It is not possible. There are bunch of processor, bunch of memory, billions of lines of code. There is no way they could be verifying rest of the lifetime of the universe before releasing a phone in the market. What they do, they give hundreds and thousands of phone for free. And those phone, those people, they will pretty much use for anything like drinking, driving, smoking, texting, they will be doing all that type, calling, voice calling, multi-people calling, people will be trying everything possible. And whichever people complain and say this is mistake, that is mistake, they will fix it and refabricate it. Apple is only one of the few company who do not care about a half% silicon failure. They do multiple fabrication before product release. They just release, instead of verify a lot, almost done, then fabricate, they immediately fabricate, find all the bugs on the real device, because then you just verify the application scenarios. If the device was not ready, you cannot ask a stranger on the street, can you come sit in front of the computer, fold your shirt and then try finding some bugs? Nobody would be interested, but if you give somebody a phone, try different ways of using it, everybody would be interested. Even kids like Om would be happy to find some bugs, try different things, play with different way, because once it user friendly, lot of people will try. And if you can cover 99.99% of the use cases, other cases does not matter. Even if somebody complains, oh my phone is not working, this and that, it is much cheaper for the company to give them a new phone than doing all these verification and basically still not feeling bad, I did not do enough. Any questions? Please participate. I am putting my best foot forward. I want each of you to do that same as a respect to me.
Sir,
yes, please.
One question.
You
from
made me
my
happy.
side.
Go ahead.
When we are talking about security perspective, basically in GRC, there is a concept of risk management in which we analyze the risk, and based on some metrics we put forward our decision. Either we have to avoid it, transfer it, or we have to mitigate it. So I am thinking in that way. Many companies do not do verification on a large amount because they know that the risks which is coming to them has not been that much higher
compared to if you spend energy. Absolutely, absolutely.
So they basically avoid the patching at the earlier time, and after releasing in the market, they came up with the feedback, and based on practical approach, they are patching the system. That
Absolutely.
is much convenient for the company and much
Absolutely.
convenient on the user side.
But we can't do that for airplane.
Yeah.
Airplane is flying, something went wrong and then you are patching on the flight, that is not going to happen. That does happen once in a while, and there are 3 incidences where the landing gear did not engage, actually did engage, but the tire supposed to be this way, tire became this way. So, if it lands, it would keep rotating, an accident. So, the mechanism is, it is all well known thing, you have to keep on flying to burn the fuel, or you have to somehow open the fuel tank and release the fuel down. So, it is going to do crash landing. If fuel tank is on, it's everybody will die. If fuel tank is not on, the explosion will not happen, some people will die. But anyway, that is a different story. So, the reason airplane or any safety critical systems, all the use case scenario that is possible, that they exhaustively test, engineer test, company test, then Federal Administration Aviation requires that there is a third party, independent third party with whom you are not having tea and coffee, they will do their evaluation. So, there are multi-layer of evaluation, all the use case scenario, that is how it works. I am coming back to the story now. So, typically there are 3 scenarios. Dr. Korfa yesterday talked about manufacturing testing. So, many companies, there are thousands of engineers, they are just focusing on manufacturing testing. Most of the energy people try to put on the before things get fabricated, because it much faster to fix, less expensive. But after fabrication there are 2 community. This community believes it is functionally correct, there could be manufacturing defect. This community believes there are no manufacturing defect, there are functional bugs. But you realize both can happen at the same time. A manufacturing defect will show up as a functional bug, a functional bug may show up as a manufacturing defect, but we will not get into that philosophical discussion. So, verifying as early as possible, capture as many bugs as possible is a good thing, but verifying at this level has one good thing, everything bad, one good thing, actually 2 good things. One good thing is you are actually testing the real device on the real system. If you build a robot, robot is actually walking. So, there is one more good thing about testing after fabrication, very powerful advantage. Any of you know? Yes, please.
Sir, basically when we are making a project, there are several components, we try them individually, but when we are integrating them, then the deployment may not be that fruitful or may be diverted from the actual result. So, testing at the time of integration and after deployment is the real use case that we are providing to the customer, and we are basically testing the software
Real
on practical
product.
reviews.
Thank you, thank you. So, that is the first one I said. Second one is it actually runs at speed at gigahertz. You can run a test kit at gigahertz, this typically runs in megahertz, because that is typically simulation speed. So, create a scenario. So, for example, if you can find a bug at a gigahertz speed for few seconds, that will take almost a week to run on a simulator to reproduce or fix. So, you have a strategic advantage that you can run at gigahertz any testing you want to do, but the problem is the amount of trace it produces, terabytes of data. How do you manage? That is a different problem. So, I will skip all of that. Post silicon I talked about.
This pre-silicon has one more advantage of observability, right? So, this has less observability.
Pre-silicon also has the advantage of observability. Even if million lines of variable, millions of variable, you can put a printf, although that is unmanageable. But here, as we talked about, the trace buffer is very tiny, 128 or 1000 signals for 1000 cycles, right. But now the security perspective I want to give you. So, most people in this world have low IQ, take it from me. They will always do bulletproof door, bulletproof car, they do all of that stuff, and they have a significant vulnerability. They are addicted to drinks, drugs, many other things I am recorded, I can't tell you. An attacker would attack at that point. Why would they try shooting at the bulletproof door when you are surrounded by 200 bodyguards? Why would they do that? That is stupidity. Why would I come to your house and try breaking your bulletproof front door. I can break your bathroom door, sure it would be smelly, but my objective is not to get a good smell, to steal you, to rob you. So, I will break your bathroom door. So, breaking through this is analogous to breaking your bathroom door instead of trying to come through your front door. And it is not just in even in USA, all the front doors, everything so exotic, and whole house is made of glasses, and I never understood, I do not want to understand, but I am just saying it is an attacker's paradise, everything. So, now let me zoom in to little bit of validation verification story. What are the underlying principles that makes it happen? But before that, I want to ask you a question, because if you guys are not answering, I will fast forward. So, you have two things in the context of verification. One we call as specification, something that is given, something we assume as correct. So, whenever your professor gives you a project description, the English document, that is your specification, and when you implement your project, that is your implementation. And in English, if I have to kind of talk about what it is, does implementation satisfies the specification? That is what we are trying to. A verification basically means whatever you implemented, does it satisfy the specification? Assumption is specification is correct. Many times it is a important legitimate question, how do you know specification is correct and who corrected it, how did I verify it, because nobody else to compare it with. Let us not discuss that today, we can discuss that offline. Let us assume we have a model that we know as golden. So, when I do 2 plus 3 and expect a 5, the golden model is in my mind, somebody told me 2 plus 3 is 5. Or you can think of this could be a C program and this could be a RTL, some gate level, some kind of hardware description, language description, detail, or it could be RTL, this could be get implementation after synthesis, this could be C program, this could be assembly. So, whichever way you look at it, or the first one could be C, second one could be C by running through Professor Korfa's the tool that insert the masking logic and all that stuff, power security aware implementation. So, functionality did not change. So, we are trying to see does implementation satisfy the specification. In this context, I am going to ask you a question, I need some space, or W will work. So, in this context, which one is true? I implementation is equal to specification, I is a super subset of specification, or I is a superset of specification. You have to raise hand at least for one of them, and please say which one you believe. One, how many of you think when I say implementation satisfies specification? Let me write it for you. This is the context. Implementation satisfies, does implementation satisfy specification? That is really the verification question. How many of you think 1 is correct? I have one hand. How many think 2 is?
Actually, I am going for 2.
Oh, no, wait. 1, raise hands. Nobody. 2, because in my class when I ask, I have 300, 400 people classes. Before people raise hand, they look left. It is good that nobody is looking left and right. 2, 1, 2, 3, 4. So, this is 0. Here I got 4. I will add up. You know, I know mathematics. I will add its total number 3. 3, 2 hands, 3. It does not add up. The number of people in the room is 20. 4 plus 3 is not equal to 20. So, let us try asking those of you said implementation is a superset of space. What is the rationale? 3, how many of you raised hand? Explain to me.
Sir, with the simple notion that if implementation should at least be equal to specification. So, it can give me more things, more features or more capability, but at least the specification part should be there in the implementation.
Okay, who else raised hand for this one? Yes, what was your rationale for choosing this?
I think the same, the implementation could be more than just the specification.
Okay. So, most of my students answer always give implementation is this big, and this is implementation, specification is this small and tiny. So, therefore, this relationship holds. If I did not give anything, this argument is fine. If I gave this, I satisfies S. In the master slave model, who is master, who is slave? I is trying to satisfy, make happy S. S is the master, I is the slave. How can I be more important, bigger? So, this is not an answer. Equality, we are trying to go there, this is the correct answer. So, let me get into this relationship. So, let us take the adder example, it is easy to understand. If this is the whole space of adder, you already know some adders, right? Carry look ahead adder, ripple carry adder, half adder, so many of these adder, and then the question mark means there are other implementations adder algorithm possible that has not been invented yet. So, it is a huge space, but the one you implemented, let us say you implemented ripple carry adder, but even then it does not cover the whole space of this, because this one says ripple carry adder of anything. Remember, specification is C equal to A plus B. When you say A plus B, first you did not say it is a ripple carry adder, you did not even say it is a 32-bit addition, you did not say it is a integer addition, floating point, you did not say anything. So, when you do not say anything, it actually from a verification context, it represents a bigger space. But implementation customized everything, it is customized to ripple carry adder, then it customized to 32-bit, and it probably customized to integer, 2's complement integer. So, it is a really a tiny scope you implemented, and that is why, and tiny scope you are verifying, and you guys arguments about it might have more. It's from a social engineering perspective, it makes sense. Your customer asked you to implement something, you implement more, it's great. From a verification perspective, it's a bad idea. From security perspective, it's a very bad idea. It should have nothing more, nothing less. Anything more means that's the funny thing, probably an attacker's malicious implant, right? Any questions? Verification is actually very interesting, if you kind of put your mind to it. Now, there are two ways of verifying: simulation based validation, which is I am going to subsequently talk about whole day. Assertion based validation is one of them. There are many others, and simulation all of you do, right? When you implement your project, you do simulate before you submit to your professor or teaching assistants to review it, right. So, this most of you do. So, I am not going to spend any more time on simulation based validation except some comparison. I will spend little bit of time on formal verification, so that you kind of see what that is. Simulation, you can simulate any size design, whether it is a million line design, billion line, it may take a long time, but you can. But formal verification you cannot do. I know I did not talk about it, what it is. It is a mathematical proof, it gives you a guarantee, complete guarantee of verification. How, what, I will zoom in a moment. Simulation does not give you any guarantee. Remember the adder, we can't even completely verify the adder, there is no guarantee. All you can say, I did my project and I ran 2 test cases and it worked for those 2 test cases, that is all you can say. But formal verification does not care about inputs, but it cannot deal large designs. So, that is why company always applies to small and critical components to completely verify, like cache controller, floating point unit, if you want to do adder, because those adders also important in cryptographic algorithm or some cryptographic functions, because those are security, like bodyguard, you want to make sure your bodyguard's body is strong. So, all these cryptographic algorithms, those they completely verify to guarantee. Now, I have a question, again I am expecting all hands here. To me it seems like both are equally bad, both are bad persons. This does not give any guarantee, this cannot run large designs, but company have large designs. So, as far as I am concerned, both are useless. How many of you can say what I am saying is wrong? What I am saying is wrong. Both are not equally bad, you have to prove to me both are not equally bad. They are bad in a complementary way, which is they help each other. Yes, please.
Sir, I think that they have their own merits, such as the validation, the simulation based validation that can be done in a real life scenario with the hardware and actual practical.
Let me pose the question again, I know where you are heading. So, I am dealing with 64 bit adder. No, I do not want to deal with 64 bit adder, I want to deal with 2 bit adders, right. So, then I have a tiny design, only 2 bits, 4 scenarios, I can try all these scenarios. So, I have complete functional guarantee using simulation. This dude is also guarantees only small designs. So, to me both are equally bad. I am playing devil's advocate.
Sir, but
You have to correct me. This is also can guarantee for small designs, this also can guarantee for small design, both are useless for real world.
But sir, after the implementation has been carried out, I need to do a validation of that using simulation based. Formal verification is on the paper, what I understand.
No,
So-
formal verification is also not on the paper. Okay, so let me say the bottleneck of this one, let me write it for you. Input space complexity, number of inputs, input space complexity is the problem here, and this is design space. Think of finite state machine, state space complexity. This one does not care about inputs, how many inputs you have, because it does not simulate, but the state space, think of a finite state machine, how many states, state transition, unrolling, all that stuff. So, theoretically you can have a design which has a lot of inputs, but very tiny state space, then formal verification is perfect. So, they actually complement each other, that is what industry uses, and that level of understanding is enough for rest of the day. Yes, please.
Firstly, I will ask you a question.
You should start answering my question before you keep asking me questions. Go ahead.
So
Go ahead.
why do you think in large scale formal verification will not work?
Because as we go along you will see how formal verification work. It creates the state machine and then keep unrolling the state machine. So, wait for until the break time maybe, or maybe we will start right now, it will answer that question, how it operates, what does it do, then you will understand. Any other questions before we proceed? Okay. So, now that we understood about simulation based validation, I am going to skip all of that. Think of your project, whatever tests you generate and all that, I am going to skip that. Formal verification, there are many, I am going to just let me try in 7 minutes 7 techniques. There are, so my objective is not to get into the detail of any of them, and in fact just model checking is a full semester course in University of Texas at Austin. So, I will not even attempt to give you clear idea of what this is, it is just you get a rough idea what does it do. And the inventor of model checking actually got the Turing award, 3 of them, and that is treated as a Nobel Prize in computer science. So, each of them is, and also SAT solving, those of you are from algorithm area, you know, is such a powerful thing, you can use it everywhere. Not only that, complexity theory people, whether they try to map satisfiability problem into that problem to prove what is the complexity of that problem. So, these are all powerful things. Let me just walk you through, so that when you next time hear that word theorem proving, you kind of know what the hell are they talking about. So, theorem proving, I will take a silly example. So, we have a set of rule, father x y, meaning it is a parent and x has to be male, right. So, if I give you a set of rules and then I ask you a question, is Bill uncle of John, that is yes, if I can't even see Sue is uncle of John, that would fail. And the way theorem proving works, and you guys have done all of this unknowingly in your 8th, 9th, 10th grade, you probably prove that left hand side equal to right hand side. Most of you start with left hand side, keep going, and then you eventually say right hand side, and hence the proof. Or before I do, let me ask, how many of you can prove a plus b whole square equal to a square plus 2ab plus b square? You can come here and prove. How many of you can prove a plus 2 plus 3 is 5? Okay. So, this is theorem proving. You start with somewhere and you try to prove something, and in this particular example what will happen when you ask is uncle Bill of John, that is a node you have to prove. To prove that, go to the rule uncle x y, meaning you have to prove a rule called parent, then you have to prove a rule called sibling, and it is a add and operation, you have to do all of them, and then you have to prove a rule for male. And as you can see, male x, this is Bill, what did I do? this is Bill, and let us see somewhere it says Bill, male is Bill. So, this one is true. So, you keep on breaking each of the tree into sub tree, when all the leaf nodes would be true, then whole theorem has been proved, right. So, it mathematically breaks down the problem into sub problem, then prove those sub problems, and that is the theorem proving. It does not care about the input at all. Now, you might be saying, well, all this stuff, first of all, there you can download a theorem prover, it comes with its example, you can play with it, and I gave a silly example, but in real life if you designed a processor, let us say RISC-V processor or a version of RISC-V processor, if I asked you, can you prove that this has in order execution, before I prove, can any of you give me an English sentence to spell out how do I write the theorem? Proving is later. What are we trying to prove? In order execution is the in English full sentence. Can any of you tell me what exactly I have to prove? Before we convert that to mathematically, give it to a theorem prover. You give the design and the theorem. So, you give the design, and if I can formulate this as a theorem to the theorem prover, and theorem prover will basically either say yes, theorem is proved, or say nope, here is a example, we call it counter example, where it fails. Then you can, a designer can take that counter example, try to fix the design. How do I write this in order execution? Yes, please.
In English, sir, I am trying to prove that root left right is the sequence of execution.
Okay. So, if I spell that in English, non-English, if there are two instruction II and IJ, any two instruction randomly separated by random delay, then if this is the case, then I am going to say in this particular context I am going to say the start time, if start time of II is less than start time of Ij, then the end time of II should be less than equal to end time of Ij. Then if you give that to the theorem prover will prove it for you. So, the theorem proving problem is theorem prover is very robust these days. It may stop once in a while and you have to say, oh, did not you know for integer additions 2 plus 3 is actually 3 plus 2, the kind of associative rule applies. Sometimes theorem provers get confused, you might have to put some lemmas in there, some stuff that it is supposed to know, for that context, that scenario it does not know, you have to provide it, right. So, this is basically theorem proving. Mathematically it proves it, deals with bunch of equations. So, this design would be converted to bunch of equations or formulas, theorem would be bunch of formula, it deals with that formula, and basically what the way it constructs the tree and too many sub trees. Now, going back to your question, because it is constructing the tree and the scenarios, if the design is complex, the scenarios are complex, that scenario tree would be so big, it is not going to fit into the memory. We call that state space explosion, and this will be even more clearer when after the break we talk about model checking. We stop here. Thank you.